We have already understood the meanings of cost function and gradient descent, right? So cost function is basically the measure of the error that is there in the regression, and gradient descent is the method through which we minimize this error, right? This is in summary what we do. And let's say we are trying to minimize the cost function with respect to a certain parameter. Let's say A1, considering our equation is like this, A0 plus A1x, we are keeping it simple for now. Simple linear regression, we are keeping it. So we are going to have a cost function in the beginning somewhere here. Let's say here is the cost function, and slowly what will happen is we will, through gradient descent, we will reduce it and we will stick to the minimum value. We will not go upwards like I have drawn here. We will stick here. We'll stick here. This is the minimal position, right? Cost function minimum. And at this position, the criterion is that del j of del A1, that is j differentiated with respect to the slope, the respective slope that we are considering, has to be equal to 0. This is the criterion. And A1 in this position, the A1 value is measured like this. A1 is equal to old A1 minus alpha into del j del A1. So we do this like stepwise, from here to here, then here, then here, then here, then here, and slowly we come down. And this step size is decided by what? This step size is decided by alpha. This alpha is called learning rate. I am just recapping the things so that we have to understand a few more things before we get into ridge regression and lasso regression. So I am just recapping a few more things, right? So this is how we have understood cost function and gradient descent. Now, friends, we have to understand a few more things. What are those things? First thing we need to learn is bias. Second is variance. And third is regularization. Okay, friends. So first let's understand what is bias. Let's say we have a training data set like this, right? We have a training data set like this. This is the Y, this is the X, and these are the data points for the training set. Now we are trying to draw a regression model through it. Now somebody suggests that the regression model should look like this. Now obviously, simply looking at it, we can understand that this is not a very good fit. Even in the training data, the performance of this regression is not going to be very good. There will be lots of errors, very high level of errors, and obviously the cost function has not been minimized here. So the observations can be in this one: performance in training data not good. Performance in training data not good at all. We say this data has a high bias, or this is an underfitted data. High bias or underfitting. This is a case of high bias or underfitting. Okay. Now let's say somebody suggests that no, this is not the regression. The regression should be something like this. Now, this looks very pretty, but the problem is, this is the training data regression that you have created. But if you use it in a test data, then there are high chances this regression will not do well at all, right? Because it is overfitted. It is very well fitted in this data, but if you put some other data points, the regression may not fit at all. This kind of data, which is doing very well in a training data set, but has very less chances of doing well in test data, we call this a data with high variance, or it's an overfitted data, or it's a case of overfitting. So performance in training data, brilliant, but performance in test data not good at all. This kind of data is said to have high variance or this is said to be a case of overfitting. Now friends, what is the way of us solving these problems? How do we solve the problem of high bias? How do we solve the problem of high variance? Like, we cannot have extremely high kind of, we cannot have a regression which performs almost perfectly in a training data and performs miserably in a test data. And we cannot have a data obviously which does not perform well in the training data itself, right? So we have to find a way out. So what can be the solutions for a high bias, friends? The obvious solution is we have not minimized this data. This regression itself shows that the cost function is not minimized. So we do further minimization of cost function. Minimize J. Second is look at using more variables. Maybe your equation does not have enough variables. Add variables or features, right? Third is, if either of these are not working, try using a bigger sample set. Say if you're using 500 worth of data, try using 1000, 2000, 5000 size of data set, right? So these are the simple solutions that you can use to reduce bias. Here we have assumed that regularization we have not done while doing the regression. We are just using simple regression formats, right? So this is about the bias. So these are high bias solutions, high bias resolutions. Now we will be talking about high variance problems. So solutions for high variance. Firstly, look at changing the model. Changing the model, you have maybe made it more and more complex. Changing the model. Maybe reduce the number of x's. Maybe change the equation itself. Right, this is something you can do. Let's assume you have 1000 features. You have 1000 features which are explaining the dependent variable or the y. In this kind of a situation, you do not know which variables to keep, which variables to let go, or which variables to reduce significance of. You do not know them. What model of equation, you have no idea how to change the model to make it more efficient. So you are not going to be able to do it manually, right? So in this kind of a situation, our solution is something called regularization. Here in this class, we will talk about regression, which uses regularization as a part of improving its efficiency or its performance, both in training data and testing data. And we will talk about three kinds of regression in this context. One is ridge regression, one is lasso regression, and the other one is elastic net regression. So we will do all these kinds of regression hands-on, and in the process explain them also, how they work and what are their advantages, disadvantages, etc., etc. Right? So let's get on with it. So first we try to understand ridge regression, what this does. Now in our regression format, let's say in the linear regression format, we found out that the cost function looks something like this: 1 by 2m sum of y hat minus y whole square, and this is the sum, is basically the sum of all the sample values. M is the number of samples. This is what we found out as our regression cost function, right? But here the problem is there that we do not know which of the parameters or which of the variables are useful and which of the variables are useless or less useful. We do not know that. So let's say we have an equation like this: y is equal to a0 plus a1 x1 plus A2x2 plus A3x3 plus dot 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 plus A n x n. N is the number of variables, right? Number of x's, that is. Now we do not know what to do with them, how to reduce the model. All we are finding is that the model is getting overfitted, right? So what do we do in such a case? This is a linear regression, mind you. This is not a non-linear regression. So just to give you an example of how overfitting happens in linear regression, let's look at this one. Let's say there are points like this. In your training set, you have points like this. And your regression model has worked out to be like this. We are using a simple regression data, right? Now, you use a test sample. From the same pool of data, you took this training sample data, and now you are applying the same regression set on the test sample. The test sample looks something like this. So obviously the sample fooled you. You did not get the accurate representation through your training sample, and the test data is now in a condition where it is underfitted, right? The regression is not working very well. So the error in the training set was very low. The training set performance was fantastic, but the test set performance was nothing to talk about, right? This was the situation. So this is a situation of what? High variance. High variance. Now here we are assuming this kind of a situation only the dimensionality has increased to n dimensions, right? Here there is only one dimension, y, and one x. But this can also happen when there are n variables. In fact, when there are n variables, there are higher chances of overfitting. So that is what has happened. We are assuming this. Now what do we do? In this kind of a case, what do we do? What can we do is, we can reduce the power of variables which do not have much impact or are not required much. How do we do that? We add a factor to our cost function expression. We add this factor plus lambda multiplied by sum of aj square, and j is from 1 to n, that is all the slopes, all the slope coefficients, these ones, excepting this one. We do not take the intercept a0, except that all of them we include in this lambda multiplied by aj square sum expression, right? So this is what we have added. Now what do we get out of this, friends? Let's say we are trying to do gradient descent, right? So we are trying to do gradient descent, let's say with respect to A2. We have chosen A2 as our example here. New A2 is equal to A2 old minus learning rate multiplied by partial differential of j with respect to A2, right? If you simplify this, it becomes like this. Alpha into, once we differentiate or partially differentiate with respect to A2, this expression, this j expression becomes something like this. 1 by m sum of y hat minus y multiplied by x plus 1 by m multiplied by lambda into A2. This is what remains. In the second expression, only the A2 remains. Now if we further simplify it, this becomes something like this. We take this expression outside. This becomes A2 multiplied by 1 minus alpha by m into lambda minus alpha into 1 by m. This is like the previous regression examples only. The second expression remains that way only. Sum of y predicted minus y multiplied by x. This is how it remains. Now we had spoken in the last chapters about cost function, how to choose alpha, that it should not be too big, it should not be too small, it should be optimized, right? Because if it is too big, the cost function finding becomes difficult because it keeps on zigzagging like this. And if it is too small, then it takes too much time it takes to come to the minimal. So none of these are desired, right? So we need an optimized level of learning rate. The same concept goes for our lambda. We have to choose it very carefully, friends. So how do we choose it? We choose it through something called cross validation. That is, we select a range of lambda values. Let's say 1, 2, 3, 5, 10, 20, 30, 50, 100, 1000, like that. We choose a bunch of values, and then for each of them we do the cost function minimization, and we choose that value of lambda for which our regression does best in the test data, right? That's how we choose it. Now, a very uncanny thing happens when we try to choose this lambda and do the cost function minimization. So let's do it only for A2. We can actually demonstrate this for cost function minimization with respect to all the variables, right? So let's say initially when lambda was 0, the cost function looked like this. This was the minimal point. This is the value of the slope is 0 here. 1, 2, 3, 4, 5, 6, 7, like that. And this was the cost function, right? Here it is the cost function. This is say A2 only. We are just taking A2's example here. Actually all these coefficients will be optimized to minimize the cost function. Now this is lambda 0. Now let's say when lambda is 1, this changes to something like this. This is for lambda is equal to 1. Now we do it for say lambda is equal to 5. Again the regression changes and it becomes something like this. This is for lambda is equal to 5. Again we do it for let's say 20. Okay. We do it for 20. So something peculiar is happening. We will discuss it in just a short while. Now we do it for 50, let's say. Then ultimately we do it for 100. Now you can see uncannily the slope is moving towards 0 but never hitting 0. Through ridge regression, what we are finding is the slope is moving closer and closer to 0, this side. This side it is tending towards, but it is not hitting exactly 0. It is moving closer, 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 further closer. Now, is it the criteria that it has to be the closest to 0? No, that is not the criteria. The criteria is out of these multiple values, the instance in which the test data performance is best, we choose that one. We do not choose the one which is closest to 0. No, that is not the criteria. The criteria is for the value of lambda, after doing the regression or after doing the optimization for all these coefficients, the value of lambda which gives us the best regression performance in the test data, that value of lambda we choose. It may not be closest to 0, not necessary. Okay, let me write it. We choose that value of lambda for which our test data regression performance is best. Simple as that. Okay. And one more thing, when do we use ridge regression, friends? we were saying that there are multitude of variables, we do not know which one to get rid of and all that, but let me be very precise now. We choose ridge regression when we know that most of the variables are useful, but we want to reduce the impact of many of them. When do we use ridge regression, friends? When we know that most of the variables that we have used in the equation or in the regression model are useful, but we want to reduce the impact of certain variables for maximized performance in the test data. That's when we use ridge regression. Now, what if most of the variables that we have used in the model are useless? In that case, what do we do? In that case, we use something called lasso regression. That is the next discussion point. Now, before we move on, a few clarifications. Can ridge regression be used for classification? The answer is yes. Can regression be used for nonlinear regressions? The answer is yes. Regularization can be used for classification also. It can be used for nonlinear regressions also. Even in case of neural networks and deep learning, we use regularization of this kind. Okay, friends, now we move on to lasso regression. Even for that, these hold true. They can be used for classification, they can be used for linear regression, they can be used for non-linear regression models also. Now let's begin the discussion for lasso regression. So this is our cost function. We have taken the example of multiple linear regression model only with n variables, y is equal to a0, a1, x1, a2, x2 up till an xn, and this is our cost function, right? Now for lasso regression, what is the modification that we do? Like in ridge regression, we did something, right? We added a square value with a lambda and did something with it. Now here also we do something like that. What we do is we add lambda multiplied by the sum of the mods of the slopes, right? This is our formula for lasso regression. Now here again something very intriguing happens, friends. Let's look at it graphically. What happens? So we are going to change, let's say A1 this time. So the new A1 is equal to old A1 minus alpha into del J del A1, right? We are partially differentiating it. Now within this we have our lambda, and this lambda we are going to choose a range of values for it, right? Like we did last time, 1, 2, 3, 5, 20, 50, 100, 500, 1000, like this we are choosing values, right? So if we plot the graph, then there is a different peculiar behavior that we see this time for lasso regression. What it is, let's understand. So we are trying to do a gradient descent for A1 here in our example. Here is 0 value of A1, then 1, 2, and the cost function is in the vertical axis. Now for lambda is equal to 0, let's say the gradient looks like this. This is for lambda is equal to 0. So the minimal point is here, right? Now let us increase the value of lambda and let's see what happens. Let's say at lambda is equal to 5, we want to see what happens. Lambda reduces. Now the gradient descent happens till here, till the point where 0 is reached. Then there is a kink which happens, a bend happens, and the curve goes like this. The minimal is hit here. Now let's increase it to 20. Let's see what happens. Again it comes down, hits 0, takes a bend, sharp bend, and goes up from here. So this is 20. This was 5, right? The minimal is here. Now let's make it 50. Again at 50, it comes down till 0, takes another even sharper bend, and goes like this. the minimal, let's say, is somewhere here. The minimum value is somewhere here. Now let's say we hit 100. At 100, here, let's say we find it directly goes up from 0. It hits 0 and directly goes up. So at 0, at 100, 0 is the minimal that is reached for the slope A1. So in case of lasso regression, the slope can be exactly equal to 0, which is not the case in case of ridge regression. It will be very near to 0, it can be very close to 0, but it will never be equal to 0. Here it is exactly equal to 0 if required. Now we have chosen all these gradient descent curves. Which one will you choose? Obviously the one which performs best in the test data, not the one which has 0 in the slope value, not necessarily, but the one which performs best in the test data, because this gradient descent we are doing for all the slopes, not only A1, right? We are doing it for A2, A3, A4, A5 till AN, and the cumulative performance has to be best. And for the cumulative performance to be best, whatever the value of lambda is required, that value or that iteration of the regression model we will choose. So when the performance with the test data is the best, that is the iteration or the lambda value or the model that we choose, right? Our objective is not to reduce every slope to 0. That is not the objective. The objective is to choose the model that performs the best in the test data. For that, whatever lambda has to do, whatever regularization has to do, whatever the value of the lambda has to be chosen, we choose that. That is not a problem, but the performance has to be the best. How many become 0, how many do not become 0, that is not our concern. Our concern is the performance has to be the best in the test data. And for lasso regression, obviously, when do we use lasso regression? When we know most of the variables that we have used are not required, do not have a significant relationship with y. When most of the variables that we have used in the model are not useful, that is, that do not have significant relationship with y, that is when we use lasso regression. Now, a ridge happens when most of the variables that we have used we know are useful. Lasso happens when we know that most of the variables that we have used might not be very useful. Now, a third case is we do not know how many are useful and how many are not useful. Then what do we do? Then there is an alternative to ridge and lasso both, that is called elastic net. We use that. Elastic net. This is basically another modification of the same cost function. Let's say we take the example of our linear regression model only. This is 1 by 2m sum of y hat minus y square, right? So here the modification that we do is we do not know whether to use lasso or ridge, so we end up implementing both. Lambda into sum of aj squares plus lambda into sum of aj mods, that is the mod of the slopes, sum of mod of the slopes, and we put a bracket here because the entire expression is divided by 1 by 2m. Now this is the expression for elastic net. So in particular cases it behaves as a ridge, in particular cases it behaves as a lasso whenever whichever is required. That is how it performs. So this one, when do we use it? When we do not know whether to use lasso or whether to use ridge. And because this is iterated by our machines, they behave sometimes as a ridge regression, sometimes as a lasso regression, and after multiple iterations it comes up with the best permutation or best combination of slopes which gives the best performance in the data. Now some research papers claim that ElasticNet performs very well when there are too many features and too less data points. Let's say there are 10,000 variables and data points, that is M, is equal to, let's say, 500 or 1000. That is a case when ElasticNet works very well. Even ridge regression functions, but some research papers claim that ElasticNet does very well when this kind of a situation is there. The data is like fat. It is having many features, but it is having very less number of samples. Now friends, we'll go into the practicals. We'll use a very famous data, the housing data, and we will work upon that. First, we'll try to understand the data. We'll see the data, try to evaluate what the data stands for. Then we'll go into observing the data with different angles. Then we'll go into the regression, and we will do regression with respect to all these models: ridge regression, lasso regression, ElasticNet regression. Okay friends, let's get on with it. So friends, we have opened our Jupyter notebook. Here we import a few modules. Import pandas as PD, import numpy as np, import matplotlib.pyplot as plt. So pandas is for handling data frames, numpy for numbers, matrix handling, and matplotlib is for plotting charts. Also we shall import seaborn. If required, we can use it as an alternative for matplotlib. Import seaborn as SNS. Now friends, you will type this code: df is equal to pd.readXL load Boston XLSX. So this is a housing database and you'll be able to download it directly. There is no problem in that. So now you check the df. You see, you didn't have to upload any data here. It directly comes from the Jupyter notebook itself. So now you have certain parameters here: CRIM, ZN, INDUS, CHAS. We do not know what is the meaning of it, right? We do not know what is the meaning of it. Now we will try to understand what's the meaning of it. How do we do that? Let's see. So here you can see friends, the short forms actually mean certain very meaningful variables. CRIM, per capita crime rate by town. ZN, proportion of residential land zoned for lots over 25,000 square feet. In thus, proportion of non-retail business acres per town, that is industries. CHAS, Charles River dummy variable, that the river is nearby or not. NOx, nitric oxides concentration, parts per million. RM, average number of rooms per dwelling. Age, proportion of owner-occupied units built prior to 1940. So it is talking about the age of the buildings. Proportion of buildings that are beyond 1940, built before 1940, that is. So that is age. DIS, weighted distances to 5 Boston employment centers. So office areas, what is the distance from them? RAD, index of accessibility to radial highways. So nearness to highways, that is RAD, right? RAD8GH is written here. Tax, full value property tax rate per $1,000. So tax rate per $1,000. Property tax they are talking about. PT ratio, pupil teacher ratio. So we are talking about the school facilities here, PTR. B is 1000 multiplied by BK minus 0.60 to the power 2, where BK is the proportion of blacks by town. So this is a ethnicity proportion that is being represented here. LStat, percentage of lower status of the population. So lower status means lower in economics, it might be lower status percentage of population, that is mentioned here. MEDV, median value of owner occupied homes in $1,000. So this is our MEDV, is basically the Y. We want to measure the home prices from the given values of independent variables, which are CRIM, ZN, industries, CHAS, NOx, RM, age, DIS, RAD, tax, PT ratio, B, LStat, etc., etc. So now we will get on with it. So friends, before we do anything with the data, we get into the regression, we want to visualize the data a little bit. What we'll do is we will do scatter plot of every pair that is possible through the function called pair plot, which is part of the SNS module, that is Seaborn module. So that's what we do. SNS dot pair plot, the data will be DF. It will take a couple of seconds. So friends, you can see all the variables have been plotted in scatter format against each other. So let me zoom in to visualize it better. So you can see MEDV, this is the pricing, right? We will just try to see what is going on in this row itself. So for example, MEDV, if you see this with respect to NOx, NOx is 1, 2, 3, 4, 5, the fifth box, last row, fifth box. You see, as the NOx is going up, the pricing tends to go down, right? The slope is downwards. RM is number of rooms, number of dwellings, right? So as the number of rooms are going up, the pricing is also going up. Age is a proportion of older buildings, that is the buildings which were built before 1940. Here, as the concentration on the proportion of older buildings is going up, the pricing is going down. See, the concentration is going down somewhat. DIST, what was that? DIST was weight distances to 5 Boston employment centers. So distances from office complexes or commercial centers. So this is as the distance is nearer. As the distance is nearer, the pricing is going down because people do not want to, I think they do not want to spend their home time in a place with lot of din and bustle, right? That is the psychology, and so the prices are going down. Then let's come to LSTAT. Let's come to LSTAT. LSTAT means lower strata population. Obviously, you can see here, as the lower strata population is going up, the proportion is going up, this is coming down. The pricing is coming down. So we can visualize every box like this and try to interpret them. This is the way we do pair plotting, right? Now we move on to regression, friends. So our plan is basically to compare ridge, lasso and elastic net. But how do we compare? We need a basic regression, which is the linear regression that does not have any regularization. So first we'll do a normal linear regression. Then we'll compare its performance with ridge, lasso and elastic net and try to interpret the results. Okay. So first let us start with linear regression. Linear regression. So linear regression, we can import it from sklearn.linear model. From sklearn.linear model, import linear regression. Right. Now, we import something called the cross-val score. From sklearn.model selection, import cross-val score. Now, how does it work? Let us look at how it works, friends. So this was what cross-val score is. Now we will create a linear regression model, friends, but for that what we'll do is we'll split the data into x and y first. So x is equal to df dot ilog, all the rows, we need all the rows and all the columns except the last one. So column minus 1. This is the way of representing the data. Now let's see if we have our x, all the features. Yes friends, see, we have all the features separated. Now we will take out y. Y is equal to df dot ilog, all of the rows and only the last column. Now I want to take it as a data frame. So I'll do pd dot data frame and put the df ilog within this. You can see friends, we have received all the prices, right? The prices are in $1,000. So we have our prices and we have our features that predict the prices. Now we are proceeding towards creating our linear regression model. So linreg is equal to linear regression. Now we will measure the mean squared errors in this linear regression. So what we'll do is linreg MSE is equal to cross-val score, estimator is linreg, data is x and y, scoring will be negative mean squared error. CV is equal to 5. 5 divisions, right? So what will this do? This will basically split the data 5 times into 2080 splits, and for each of the samples it will measure the negative mean squared error. That is what the cross-val score will do. Now let us measure the linreg MSE, or let us find out what are the values coming. Okay. Let us find the mean for it. Mean lin MSE is equal to np.mean linreg MSE. It is minus 38.01. This is the metric. You can say this is the way we will be measuring the performance metric. So error, the lesser it is, the better it is, right? Now we will measure it for ridge regression. So for that what we do is we import ridge from sklearn. sklearn dot linear model import ridge. So friends, now we will import something called grid search CV. Grid search CV is going to give us the ridge regressor on which the data can be fitted. And the grid search CV takes in the values of the lambda, the range of values that we saw in the theory. We have to put a range of values of lambda. This is taken in by the grid search CV along with the estimator and the metric through which we want to measure the performance, which obviously is going to be negative mean squared error, and also the number of cross validations. We have kept it 5 for linear regression, we'll keep it here also 5. So let's see how we are going to do it. From sklearn dot model selection import grid search CV. We call it a module which tunes the hyperparameters, but simply put, the functions that I just spoke about, that is going to be satisfied by grid search CV. Now we create the estimator here. Ridge is equal to ridge. Now we create the range of values for lambda here. In place of lambda, we call it alpha. is the same thing. 1e minus 15. So we start with smaller values. 1e minus 10, 1e minus 5, 1, 2, 3, 5, 10, 20, 50, 100, 200, 500, 1000. We'll leave it at that. Now we create the ridge regressor or the ridge model. Let's call it the ridge model. This is equal to grid search CV. First we put in the estimator, then we put in the parameters, then scoring. This is equal to negative mean squared error, and cross validations. CV is equal to 5. Now we see the ridge model is there. Now we fit the data into it. X, comma, Y. Sorry. Dot fit X, comma, Y. Now the data is fitted. Okay. Now we find out which is the best parameter value, that is, which is the lambda value for which the performance of the ridge model is best. Alpha is equal to 200. And for that, what is the MSE? That also we have to find. Print ridge model best score 30.34. So this is doing better, right? We can see this is doing better. Now we will get into the lasso regression. And lasso regression, it is very similar. From sklearn we import lasso, learn dot linear model, import lasso. Lasso is equal to lasso, this is the estimator. Params, let us copy from the previous one only. And we'll create the lasso model now. This is equal to grid search CV. First we have the estimator, then the parameters, then the scoring, negative mean squared error, CV is equal to 5. Lasso model is there. Now we fit the data into it. Lasso model dot fit X and Y. The model is created. A few warnings have come, I think. That's okay. Now we are going to find out the best parameter, that is the best score of lambda and the respective best score. So lasso underscore model dot best parameter. Alpha is equal to 1. This is the best parameter. And lasso model best score is, so instead of writing print, we can directly write this also in Jupyter. Best score is minus 36. So again we are getting a better score, but grid search CV I think is doing a lot better. Now we'll do elastic net. From sklearn.linear model, import elastic net. We create the estimator en elastic net. This is the estimator. We already have the parameters. I'll not repeat it. Okay, let's copy the values. It's here. Now we create the model. Elastic net model. This is equal to grid search CV. First we enter the estimator elastic net, then the parameters, then the scoring. Let me copy it from here. Scoring and CV remain the same, so we can just copy it. Now we can fit the data also. X, Y. The model is there. Now we can find out the best parameter and the best score. So en model dot best parameter, alpha is equal to 1, and en model dot best score this is minus 32. So you can see, friends, that the negative value, that is the lowest, the value which is closest to 0 among these values, the best score values, is what is our choice. So in all of these cases, the value is lower than what we got in linear regression. In case of elastic net, we got 32.55 negative. In case of Lasso, we got 36.11 negative. Again, in case of Ridge, we got 30.34. So the best value that we got was in case of Ridge, because it is closest to the 0 value. And this negative error is basically the negative version of the actual mean squared error, nothing else. So the closer it is to 0, the lesser the error value is basically. So our choice finally becomes Ridge. So we do a projection with respect to Ridge and we see the disk plot value. So now we do prediction with respect to Ridge. So first we have to split the data. We do it with train test split. From sklearn.linear model selection, import train test split. X train X test, Y train Y test is equal to train test split X, Y. These are the data that we split the data from. Test size, let's say we get 80-20, so test size is 20%, 0.2. Random state is equal to 42. What does this mean, random state? Again, I'll repeat. We use the random state so that for any number of iterations, the X train, X test, Y train, Y test remain identical. So if you have test size as 0.2 and random state as 42, every time you do this split in this format without changing the numbers 0.2 and 42, you'll get identical kind of split. The X train will be identical even on the 10th time, 15th time, 100th time. It will never happen some data was in X train this time and the next time it went to X test. So that's how it is. X train, X test, Y train, Y test. We have got all the data. Now we'll be fitting the ridge. So ridge model dot fit. The training data will be fitted train comma Y train. Now the model is fitted. Now we use it for predictions. Y pred is equal to ridge model dot predict. We use the X test data to predict the Y's. Now we try to visualize the errors that are coming through a dist plot. SNS.distplot Y test minus Y pred. Okay, dist plot. So here is the distribution of the errors, friends. So the error here shows a normal distribution pattern approximately, which is ideal if you are looking at the assumptions behind a linear regression model, and ridge, lasso, elastic net and linear regression all form part of the same kind of regression. So we have been on the right path, friends. So thank you, friends. Thank you for being with me in this video. That's about it. If you like this video, please subscribe to our channel youtube.com/the AI School 333. Stick around for more videos on this machine learning course. We have a multitude of algorithms coming up in all categories: supervised, unsupervised and reinforcement machine learning. Thank you, friends. Thank you so much for being with me in this video. If you like this video, please subscribe to our channel youtube.com/AI School 333. Stick around for more videos on this machine learning course. We have a multitude of algorithms coming up in all categories: supervised, unsupervised and reinforcement machine learning. And you can also help me spread the word with your likes, shares and comments. Thank you so much. See you in the next video.